In this video, we'll talk about the Fourier expansion and what an amazing discovery found by the famous mathematician Joseph Fourier. You may be familiar with the Fourier transform, but this topic that we'll be talking about in this video is his discovery about how to decompose a function that really helps us with time series analysis of data sets. And I think you'll find this quite interesting. So with that, let's go ahead and go over to a PowerPoint presentation and we will look at this in detail. So as I mentioned, the Fourier expansion is really representing functions as sines and cosines. That's going to be the topic. And this is under the area of spectral analysis. This is a chapter 4 thing. And chapter 4 is about the frequency domain, and as opposed to the time domain. And studying time series data in the frequency domain, in addition to the time domain, really does open up a new avenue of being able to understand it even better. So let's define this Fourier expansion. We've already said that, but it's the decomposition of functions usually depending on time. So these functions usually depend on time, and the decomposition of these functions into a sum of sine and cosine terms. Now, let me just go ahead and say this here. I'll probably conclude the video saying this as well to summarize, but here's the strategy. Here's why this works. We want to be able to analyze the frequency content of a given data set. Well, we know how to, from trigonometry, we know how to calculate the frequency of sine curves and cosine curves. So if we were able to write a function that described the data set into sums of sines and cosines, then we would be able to analyze and calculate the frequency for those sines and cosines. And if we were able to do that, that means we would also be able to analyze the frequency for that data set. So that's the strategy behind this. Now the big question is, how are we planning to write a function as a sum of sines and cosines? And that's what Mr. Fourier did for us. Here it comes. It's a big function. This is not an easy slide by any stretch. But Fourier found out that for a broad class of functions, not every function, but for many functions, you can write those things as f of x equals the limit as n goes to infinity of a naught over 2 plus the sum of, here comes the sines and cosines, ak, we'll talk about ak and bk in just a minute, ak times cosine kx plus bk times sine kx. Tough way to write a function, I'll admit, but we have a reason for it. Now this f is defined over negative pi to pi, and these coefficients are given by this integral ak equals 1 over pi times the integral of negative pi to pi of f of t cosine kt dt for k equals 0, 1, and so on. So again, pretty tough. Notice we've got two f's going on. We've got f of x up at the top of the slide, and then for these ak's, it's calculated by taking the integral of a different f. So got some moving parts for sure. bk is defined very much the same, except change cosine kt to sine kt. As I said, that's a tough slide. Thankfully, Joseph Fourier did this for us. And again, if I hadn't given you the hint to start the video, you would probably wonder, why would you ever want to write f of x in terms of sines and cosines? You already know the answer to that, and it is because, well, we know how to analyze the frequency of, or calculate and analyze the frequency of sines and cosines. So if we can write a function in terms of sines and cosines, then all of a sudden we can calculate those frequencies for the sines and cosines, which gives us a huge insight into the frequency of the function. That's the strategy. So let's practice. We will do two examples, and these examples, note, will not be cyclic. There will be no cyclic behavior. For example, f of x equals x, we all know that from long ago. That's our friend the line, right? Y equals x. That's just a line that's has a slope of 1, right? So you have to wonder, what does that have to do with sines and cosines? And if you hadn't seen that formula on the slide before, you would think nothing. But we've been promised by Joseph Fourier that you can write f of x equals x in terms of sines and cosines. Let's look at that closely. Here is the formula. Another way to write x a strange way to write x, I'll admit, is negative 2 times the sum from n equals 1 to infinity of negative 1 to the n over n times sine of nx. You may be wondering where the cosine is, and in this particular instance, f of x equals x can be written as sine nx. The cosine term is not in this particular form. So, all right, apparently you can write x in terms of an infinite sum of sine terms, which is just crazy, hard to believe. As a matter of fact, let's pretend we don't believe it, and let's jump in and try to make some sense of this. Now, one issue we're going to have right away is we can't sum up infinitely many terms, so we're going to have to be content with letting the sum stop somewhere out at some m, and that's what we're about to talk about now. We're going to have to approximate that summation by summing up m terms. So that's what we do here. Here's approximation. The x is approximately negative 2 summation from, instead of n equals 1 to infinity, we'll go n equals 1 to m. Okay, let's do it then. Let's let m equal 1, let m equal 2, let m equal 3, and so on, and let's see how this goes. So for m equals 1, you take a look at this and you say, wow, that does not look like f of x equals x. I totally agree with that. This looks very sinusoidal, and of course it's sinusoidal because what did the formula say? It said x is approximately negative 2, sine nx, 2 times, and that turns out to be 2 times sine x. That's just another way to write it. That's not important, except for the fact that it looks very, very familiar. You know what sine x looks like, and if we double it, there are your values for it. So other than familiarity, it didn't matter that we wrote it in that term. I don't care what representation it is. We can see that it's sine curves. And m equals 1 is not a good approximation of f of x equals x. Let's let m be 2. At m equals 2, I still see, now what I see is 2 sine waves. And that's not a surprise because what we have here is the sum of, it turns out to be 2 times sine x plus sine of 2x. So not a big surprise. Let's go to m equals 3. I see about 3 sine waves there, and not a surprise because I see that that's broken down into 3 sine waves. M equals 4, we'll quit writing it in individual terms and let's just make a sum out of it. And when you see that, you again notice the sine curves. Notice that the amplitude is shrinking though already at m equals 4. This thing is surprisingly flattening out a little bit. M equals 5, even more so. Let's keep going. Here's m equals 6. Oops. M equals 7. M equals 8. M equals 9. M equals 10. M equals 20. M equals 40. At m equals 60. This thing is really starting to look like f of x equals x. Now, if you look really closely, you can see that you have evidence that there are still those sine waves in there, but they're just super tiny. They have super tiny amplitudes, so you can't really see them that well. Let's go to m equals 80. Even more so. M equals 100. M equals 200. Again, you can still see the tiny little bit of squiggle in there representing the various sine curves. M equals 500, and that'll be our last. And if you were to step back from your computer and just glance, you would think that that's just a straight line. Now, if you looked really, really, really closely and got a magnifying glass out, you could probably see the evidence of the sine waves. But that is for m equals 500. And wow, except for the ends, let's talk about the ends real quick. The ends at -3 and +3, what's going on there? Well, as you've seen in chapter 2 when we talked about smoothing, end effects can cause trouble. So except for the ends, we would have to admit, wow, the Fourier series expansion did an amazing job of approximating f of x equals x, which is what we set out to show. Okay, let's do a second example. Let's look at another example, f of x equals e to the x. So that is the exponential curve. We all know what that looks like. And it turns out that it can be written as the sum of sines and cosines. That's exactly what Mr. Fourier said was the case. And it's written as e to the x equals more involved. Notice the hyperbolic signs that have entered the equation. But look after the summation sign. You see it goes from k equals 1 to infinity of a negative 1 to the k over 1 plus k squared of cosine kx minus k sine x. So there's our sines and cosines. It's not important that you understand why that derivation happened, but let's just trust that it's written as sines and cosines. We're going to do the same thing as we did before and let k take on a few values, not nearly as many as last time. We're just going to give it a few values and show you what things look like. So here that is. We've got 4 plots here. Upper left is f of x equals e to the x. Upper right is what happens when you sum up the first 4 terms. That means little m equals 4. And at m equals 4, I wouldn't be all that convinced that that looks like f of x equals e to the x. Lower left is when little m equals 16, and I would have to say in that case I am starting to think that this is approximating f of x equals e to the x. I certainly see the sine waves just like I did in the example before, but I can certainly see that the amplitudes are shrinking, and by the time you let m equals 64 in the lower right plot, again, if you stepped away from your computer screen a little bit, you would think that that looks like the curve f of x equals e to the x. Again, you've got the end terms, so don't worry about the -3 and +3, but other than those end effects, this certainly looks like the Fourier expansion has once again very well approximated the function that it was supposed to approximate. So again, just an amazing discovery by Joseph Fourier. How he thought of this one, I don't know, but it certainly helps us out in the field of time series because of the points that we've made before about breaking things down into sines and cosines, which we know how to analyze the frequency content for, and that is summarized on this final slide. What does all this show? That non-cyclic type functions such as f of x equals x and f of x equals e to the x can be expressed as a linear combination of sines and cosines, which means that we can take a time series data set. If we can approximate it with a function, then that function can be broken down into sines and cosines. We analyze the frequency content of the sines and cosines, and then that lets us have an idea of what the frequency content is of the data set. So I hope you enjoyed that demonstration of the Fourier expansion. And one thing I want to really stress here and emphasize is the fact that looking at time series data in the frequency domain is really huge. We feel that it's overlooked. We feel that the time domain is given a lot of times more attention than the frequency domain, and the frequency domain is a super area to look. You have to be able to know how to interpret a spectral density plot, but that's not hard. The hard part is what Joseph Fourier did, and that was discovering that amazing, crazy formula. And after that, the highway has already been paved for us as time series analysts. And you'll see that as we go on from now on, you will see spectral density plots nearly in every analysis that we do going forward.